So essentially, from the value of this, we can understand how related the two variables are. Now the problem with this estimation, the problem with this value itself is that it can vary from minus infinity to plus infinity theoretically. So if you have very large values, suppose you have all the values in thousands, so you have plus 5,000, 6,000, minus 2,000, 8,000, that will give you a very large number, right? It will give you a very large number, and what happens is the more number of data you take, the larger data set you have, that data set size will affect this number, whether you have a small data size or whether you have a large data size. So if I, for example, take a larger data set, I take suppose 5,000 data sets, I get one number, whereas you might take let's say 50 data points, you get a different number. Whereas we are working with the same data set, we are working with the same two data, right? We are working with rainfall and agricultural output. So what happens is this, for the time being, this value depends a lot on the sample size essentially. So what statisticians came up with to counter this problem is that they divided this number with n. Now this essentially what does is sort of averages out the data set. So essentially what is average? Average is sort of like if you have 5 observations, you divide it by 5. If you have 10 observations, you divide it by 10. So you essentially scale down. Whatever data set you have, whatever sample size you have, you scale down that entire concept into a smaller number, a more representative number. And what that does is, sort of as I said, it represents the sample more without being biased of the sample size, without being a larger number simply because it has a greater sample size, or being of a smaller number because it simply has a smaller sample size. So what that does is, it removes the problem of non-representability. So what we have captured one problem, and that is if you do not divide it by n, it essentially lacks representability. Now that we have this value, so currently we have this value. So this is the value that we have right now. This value essentially we can look at, and we can understand what sort of relationship holds between the two variables under consideration. So suppose I want to make a chart of the nature of the variables. So if we have, suppose we have both as x increases, suppose as x increases, y increases. That is the observation that we had taken. As rainfall increases, the agricultural output increases, so it's a positive relationship. If we think that this relationship will hold, then most of the data set, as I mentioned before, will lie in the first quadrant and in the third quadrant. That is, most of the data set will have either positive x value, positive y value, or negative x value, negative y value with respect to this changed origin, that is the x bar y bar origin. And what you'll end up with is this value, this blue highlighted value will turn out to be positive. So this positive value, this gives you the conclusion that you have a very strong positive relationship. So you have a very strong positive relationship, and essentially this sort of representation of the data gives you a curve which looks like this. So you have a curve which looks like this. As I mentioned before, if you look at the red data points, you will have a curve which looks like this. So you will have a curve which looks like this. But suppose you have a different data set, the data set which with this orange data set, you will have a curve like this. So what does that tell you? What does that tell you? Essentially, for a curve like the orange one, if your x increases, the y will fall. So if your x increases, the y will fall. Let us see how that works. So as your x increases, y will fall. So suppose I have an observation over here. You have some amount of x and you have some amount of y. If I increase my value of x, my value of y falls. So this is essentially a negative relationship that I'm talking about. As x increases, y increases, y falls. They are in the opposite direction. So you have a negative relationship, and what that does is that it represents a very strong negative relationship. A very strong negative relationship. Essentially, this is sort of like the labor demand that I'm talking about, and the very strong positive would be a labor supply that I'm talking about. The problem with this is that this only measures linear relationship. Suppose you have data set like this. Suppose you have data set that is pretty much well balanced around all the quadrants. Then what will happen is your measurement, this blue measurement, will not be able to interpret this sort of data set. So what happens is, since this purple data set contains more or less equal number of points in the first, second, third, fourth quadrant, suppose you have 1, 2, 3, 4, 5, 1, 2, 3, 4 over here, about 3 here and 3 here. So they are pretty much balanced around all the 4 quadrants. So you might end up with a pretty low number which is close to 0. So essentially there is no such relationship between x and y. X and y can go in any direction possible, and you end up with a sort of a very small, either a very small positive number or a very strong negative number, and that gives you a weak relationship between x and y. What you interpret, the way you interpret is that there is no such relationship between x and y, they are uncorrelated. So you say that these are positively correlated. So essentially you say that if you have the first case, you say there is a positive correlation. So there is a positive correlation, and in the second case you say that there is a negative correlation. So there is a negative correlation, and in the third case where you end up with a 0, you say that there is a 0 correlation. So there is no correlation or 0 correlation, that is the two variables are not related to each other. So what we come up with is this value, this 1 by n summation of I equal to 1 to n xi minus x bar into yi minus x bar, yi minus y bar, is actually called the correlation coefficient. So this is not exactly the correlation coefficient. There is a greater adjustment that we need to make this a perfect measurement of the correlation, but this is sort of like the basic of correlation. In fact, this can be represented as the covariance between two variables. So this is called the covariance. We represent it as cov. So it's the covariance of the two variables x and y. This covariance allows us to give a much preliminary idea of how the correlation coefficient will work like.